All right. Hey guys, it is Miss Lastly and Miss Marker here for our day one of exponential functions. And we are going to go over exponential functions, just the basic like parent function, what it looks like, some key features of our graph, and some transformation rules. This should be pretty much a review from last year's Algebra 2 class. You guys have already seen exponential functions, so this should seem pretty familiar from last year, but if not, that's why we're going over it this year. So yeah, let's get to it. All right, so first off, exponential functions. These are functions that have x as the exponent. All right, so exponential functions, these are functions with an exponent of x. That makes them an exponential function. All right. Now, unlike some of our other functions, we don't really have like a nice set parent function equation because the base number, which is the number that we're raising to the power of x, can be any number. Now, the most standard one that you guys probably saw last year in Algebra 2 and the one that we're going to kind of use to do this basic graph is a base number of 2. So our standard kind of equation that we're going to look at is 2 to the power of x. Now, like I said, this is just an example of an exponential function. That base number of 2, so this is our base number, right? This is what we call the base, all right? It can be any number. It can be whole numbers, it can be fractions, it can be negative numbers, all right? So there really isn't a set like base number for exponential functions, which is why, unlike some of our other functions that we've dealt with, there is no set up over pattern for exponential functions. So those of you who are using like an up over pattern when you're doing your quadratics or absolute values, you can't really use that technique when we're doing exponential functions because there isn't a set up over kind of pattern. All right, well, let's check out what this graph looks like by filling in our table values. All right, so we'll start with their negative numbers and then we'll move up to positive. So if x is -2, that means we're plugging in a -2 for x. All right, hopefully you remember your exponent properties. When you have a negative exponent, to make it positive, you flip it, and that would be 1/2 to the positive 2, which is 1/4. So when x is -2, y is positive 1/4. All right, moving on to -1. So we have 2 to the power of -1. That changes to 1/2 to the positive first, which is just 1/2. All right. Next, we have 0. So we're going to plug in 0 for x. So 2 to the power of 0. Now, this is an important point. We're going to talk about this a little bit later, but anything to the power of 0 is going to be 1. This point is actually going to be really useful for us because even if we do change the base number, no matter what the base number is, if we're raising it to a power of 0, it's always going to be 1. So this is one of those points that's not really going to change because of a different base number. This is like the only point on the entire graph that doesn't change when you change your base number. So it's going to be one of our key points that we're going to look at in a second. All right, moving on, we have y equals 2 to the power of 1. That's just 2. And then we have y equals 2 to the power of 2, which is 4. All right, so if we're looking at this graph, or we're looking at our points anyways, you'll notice that as our x values get bigger, so do our y values, right? So we're going to get exponentially larger as you plug in bigger x values. And if you plug in bigger negative numbers, right, you're going to notice that you're just going to get a smaller and smaller and smaller fraction, right? You're never actually going to have a negative y value, right? If you plug in -100 for x, you're just going to end up with 1/2 to the power of 100, which is just some really, really tiny number, right? So we get a graph that looks kind of like this. All right, so -2, we have 1/4, somewhere about right there. At -1, we have a half, right? 1/2. At 0, we have 1. At 1, we have 2. And at 2, we have 4. So this is kind of what we have going on for our function right here. So like I said, if you, no matter what you plug in for x, right, if you're plugging in really big negative numbers, it's never actually going to be a negative y value. You're never going to get a negative y value. You're also never going to actually get 0. So that's going to create a line in our graph that we're never going to cross. And Miss Marker, what do we call lines in graphs that we never cross?
Asymptotes.
That is correct. You guys know all about asymptotes, right? So we're getting really close to that x-axis. Never going to cross it. And then we're going to kind of go up and curve this way and keep going up for forever. So we have that imaginary line that we're never going to cross right here at y equals 0 as our asymptote, right? And then the rest of our function is going to just grow up in the positive y direction. All right, so there's a nice kind of, I guess you could say, a parent function, right? There's no transformations here, right? So changing the base number, this is not a transformation. All right, so changing this base number, changing base number is not a type of transformation. All right, a lot of people think that it is. So if I were to plug in a 3 instead of a 2, that doesn't mean that I dilated my function by 3. If I were to, plug in a fraction, it doesn't mean I'm dilating it by a fraction amount, right? Changing the base number is not a type of transformation. It's just a different starting function than the y equals 2 to the power of x, right? So that's one thing that I see students do a lot of times. And we'll look at transformation rules in a second later on in the video, but changing the base number is not a transformation. It's just changing the base number of our function. Yes, it is going to change the points of our graph, all of the points except 0, 1, that will stay the same, but it isn't really, we're not dilating by anything. So please just make sure you know the difference between a real dilation versus just changing the base number. Okay, so getting down to our key features of our graph. All right, one we've kind of already talked about. Now, when we're looking at like quadratics or absolute value or even square root functions, we have what we call like a vertex or like a starting point. Exponential functions don't really have a vertex and they don't really have like a starting point because they do go in both directions for forever. But there is a key point that we've already talked about that is really important with exponential functions, and that is the point 0, 1. So no matter what your base number is, you will always have that point 0, 1 included in your graph. All right, so when we are doing like a vertex for a quadratic function, and that's kind of where we move that point and then we continue to like draw our graph using our transformation rules, that's going to be the point 0, 1 in this function. So we're going to treat that point 0, 1 as if it was like a vertex or a starting point in a square root function. All right, so when we say starting point or intercept, we're talking about that point 0, 1. So in exponentials, that point 0, 1 is very important, right? No matter your base, right? No matter what your base is, you will always have this point. Okay, now it does move, right? When you shift something vertically or horizontally, it can change where that point is located, but just know that 0, 1 is like that starting point, that vertex of kind of our exponential graphs. Okay, next thing that is a key feature of our function, we've already talked about a little bit, is that horizontal asymptote. So all exponential functions are going to have a horizontal asymptote. For our parent function, without any transformations, it's at y equals 0. So horizontal asymptote. All right, y equals 0, right? And again, just like when we have our rational functions and we transformed it, that asymptote can change depending on any vertical shifts or dilations or things like that. But we're always going to have some type of horizontal asymptote. All right, next up is our domain and range. So when you're looking for your domain, remember this is all the values that x is allowed to be. Well, in this function, you're allowed to plug in anything you want for x. You can plug in negative numbers, you can plug in positive numbers, you can plug in fractions, you can plug in 0. There isn't anything that x isn't allowed to be. You can have any number you want as an exponent. So our domain is going to be all real numbers. So we would say negative infinity to positive infinity. All right. Now our range is going to be slightly different because we don't cover all the y values, right? If we start our graph from the bottom and kind of move up, we don't have any y values in this bottom section, right? There are no y values. Our graph doesn't go down there. Our first y value that we really kind of come to is right around this asymptote. Now we're never going to actually cross this asymptote or touch this asymptote, but it's kind of where our graph starts and then continues to kind of move up from there. So our range is starting kind of at 0. Now we don't include the point 0, so we are going to use a parentheses, but it starts basically like right after 0, and then it does go on to positive infinity. So that's our range. Okay, so those are your key features of your exponential function. Remember, the base number doesn't have to be a 2. It can be anything it wants to be. All right, that doesn't mean that there's a transformation. It's just a different base number. Okay, next up, we're going to look at something called Euler's number, which you guys did a little bit of investigating on in Algebra 2. I think you guys did this when you were looking at compounding interest rates with, I don't know, like your exponential functions last year in Algebra 2. We're not going to do too much with it, but I do want you to get the concept of what E represents. So E is a number. All right, I know it's a letter, but E is technically a number. All right, so think of E kind of how you think of pi when you're doing geometry, right? Pi is a symbol, but it represents the number 3.14, blah, 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 right? That's the same as this number E. So it is technically a number. We just use the symbol or the letter E to represent this number. All right, so to calculate Euler's number, it's actually this really gross formula. It has limits, and I know you guys love limits. All right, so E is the limit as x goes to infinity of 1 plus 1 over x to the power of x. Beautiful formula. Like I said, you guys actually derived this formula last year when you were doing your exponential functions unit. We're not really going to do anything with this. We're going to be honest with ourselves, and we're not doing anything with it. But I do want you to know that it is a number. It's approximately 2.71827. It's a number. 2.7 is all I actually remember from Euler's number. But yeah, so when you see E, just know that, yeah, okay, it's weird, but it's just a number. Just like pi was really strange at first when you first saw the symbol for pi, but then you learned it was just 3.14, and now you're cool with it. Same thing with Euler's number. It's just a number, roughly 2.7 approximately. All right, now it is used a lot in exponential and logarithmic functions. It's what we call the natural number, or when we get to logs, the natural log, because it has a lot of applications if you're looking at exponential growth problems or investments and interest rates, things like that, which is why you guys learned about it last year with interest rates in Algebra 2. We're going to use it mostly just to change up our problems and make them more exciting. But you will see E used a lot in calculus as you guys kind of move forward into your classes for next year. Okay, so I want to talk about briefly some transformation rules. Just a reminder, so when we have our exponential functions, our transformation form kind of looks like this. So we'll use 2 as our base number. So we have x minus c over b plus d, whatever, our letters that we have in there. All right, so just like all of our other functions, things that are on the outside of the function, those are going to be your vertical transformations. So a and d, those are happening outside of the actual function. So these are going to be, like I said, our vertical transformations. There we go. pink for vertical. All right. And then everything that's inside of our function, those are going to be our horizontal transformations. So that's going to be your C and your B. So these are our horizontal transformations. Okay. So A is a dilation. So this is a dilation. D is a translation, right? Moving up and down. C is a translation. That's moving us side to side. And B is our dilation horizontally. Okay. So nothing really has changed, but I know that this is a weird looking function. So maybe inside the function versus outside the function is a little harder to figure out, which is why I kind of wanted to look at it with you guys real quick. Okay, let's do an example problem for transformations. So here we have f of x equals 2 times 3 to the power of x minus 1 minus 4. So we want to determine the transformations that occurred. We want to find the indicated values over off to the side. So like our transformations are intercept, or asymptote, domain, range, and then we want to graph. Okay, so first thing I'm going to do is I'm going to kind of go through and highlight my vertical transformations versus my horizontal transformations. So anything outside, so the 2 on the outside, that's going to be a vertical transformation. Same with the minus 4. All right, so this right here is dilating. This right here is translating. All right, so my transformations that I have so far, I have a vertical dilation by 2, and I'm going down 4. All right. Internet's a little slow. At least we have a video. All right. And then we can look at our horizontal. So those are things happening inside the function. So in our exponent, and that's going to be our minus 1. And that is going to be a translation. All right. So dun, dun, dun. We also are going, now remember, horizontal is always kind of the opposite of what you think, right? So if it's a minus 1, it really means we're moving in the positive direction by 1. So we are going right 1. All right, and those are all of my transformations. Remember, the 3 is not a transformation. It is just a different base number. Okay, so next on our list is to find the intercept point. All right, so normally that intercept point is at 0, 1, all right, but we are going down 4 and we're going right 1, and we're also vertically stretching by 2. Okay, so, all right, let's see. Do we want to dilate first? I always suck at this. There's gonna be some trial and error in this video, guys. Just, I think we want to dilate first and then we'll move. I think that's what I'm gonna do. We'll see if it works. We'll double check our answer with the calculator. All right, so usually we're at 0, 1. All right, this is our point. 0, 1, right? And so we have a vertical dilation, which is going to affect our y values. So we're going to take our y value and we're going to multiply it by 2. So that should put our new starting point at 0, 2. All right, so now we're at 0, 2. So now we need to go down 4 and to the right 1. So 0, 2 here, right? Now we need to go down 4, 1, 2, 3, 4, and to the right 1. That should be our new starting point. And if you're ever unsure, you can always just plug in 0 for x and kind of see what happens, right? Or figure out when, not 0 for x, you would want the exponent to be 0. So if I were to plug in a 1 for x, so that would be 3 to the power of 0. So that's 1, 2 times 1, and then that's 2 minus 4, negative 2. So we are negative 2, and we did go over 1. That is correct. And if you don't believe me, we can triple check on our calculator and make sure it goes to that point, which I am going to do because I want to make sure I tell you guys the right information. 3 to the power of x minus 1 minus 4. And let's go to my table. Do I have the point 1, negative 2? Yes, I do. We did it right, guys. Okay, so when you're doing these, dilate first. Dilate first before you move your point. All right, cool. We figured it out together. I thought that was the right thing to do, but I wasn't 100% certain. I should have just went with my gut, but we got it. So anyways, our intercept point is this point right here. It is at 1, comma, -2. All right, now the asymptote. Now, the only thing that's really going to affect your asymptote is that moving down by 4. So our new asymptote is going to be down at -4. So that doesn't really get affected by our dilation because it's kind of like a fake line, right? It was at 0 before. So if you were to multiply 0 by anything, it doesn't really matter. It doesn't change it, right? 0 times anything is still 0. So the only thing that's really affecting that asymptote's location is the down 4. So we now have this asymptote at y equals -4. Okay, now, if you want, you can go through on your calculator and pick out some other points of your graph. I don't really need you to do that. You should know what the rest of this graph kind of looks like. You know it's going to go close to the asymptote line and then grow exponentially upwards. So I'm just going to go ahead and sketch that. I don't really need you to be more accurate than that. I need the asymptote graphed properly. I need the intercept or starting point graphed correctly, and I need the correct shape. I don't need much else from you guys. Like I said, though, if you do want to get more technical with it, you can use your graphing calculator to figure out some other points on the graph, but I don't need that. It's not necessary for this class. All right, last but not least, domain and range. Domain is easy. It's -infinity to +infinity. Just because we got some transformations in here and changed our base number doesn't change what we're allowed to plug in for x. We can plug in anything we want for x, and it will give us some kind of value for y. All right, but we did change our range because we changed where that asymptote is. It's now down at -4. So our range now starts at -4. We can't include -4, so we use a parentheses, but we are now still going to go to +infinity. All right, so there's our range value. Okay, so that is it for this video. I hope you guys found it informative, and I will see you in the next one. Bye, guys.
Bye.